Previous class, we stopped at example number 8. Today, we look at, previously, what we look at is all on the x and y axis. So we have another type of coordinate system is your polar system or radial coordinate. So here we look at angular momentum, angular momentum. So angular momentum, again, what is momentum? Definition of momentum is mv, momentum equal mv. So angular momentum. Angular momentum, it will be like the concept of moment. So what is moment? Moment is force times distance. The force and distance must be perpendicular. Okay, then we create a moment, right? So angular momentum will be the same principle or same concept as moment, but it will take focus on momentum. So the momentum have an arm, then you will get angular momentum, denoted by capital H, or equal to R or D. In this case is D cross mv. Okay, so on the diagram here, you have origin O, X, Y, and Z. And then you have a particle moving on the plane of XY. So this one will move. And then you know that velocity on the curve always tangent, right? So this one you move tangent direction mv. And then you get a distance of d that is perpendicular to the vector. You will get angular momentum. Okay, so the d must be perpendicular distance or intersect with the path of your mv vector. So you take this one, if like for example, you study moment, you take force multiplied by d, right? So this one is angular momentum. You take mv cross the d, or d cross, right? But in this case, we use right hand rules. Right hand rules. You take your four fingers is your the four fingers is the d2, I mean direction of d curve into the direction of momentum. Then your thumb pointing up, right? The direction of angular momentum is anti-clockwise, going up. Okay, so this is how you analyze the angular momentum. Use right hand rules. Always take distance times or cross the mv. Okay, so you know that this is vector. So vector, you have magnitude and direction. So this is your direction. The thumb is the direction, right? And the direction is anti-clockwise with the curve. Then magnitude, you take the d times the mv to get the magnitude, right? So, okay. Any questions so far on the slides? Clear? Okay. So the unit is distance. Distance is meter. M is kilogram. Velocity is meter over second. So you group the dimension, you get kilogram meter square over second, right? And let you sign the tendency. Okay, continue with the slides. Then previous slide was scalar formula, which you find the magnitude. You take the radius, the distance d times the mv. But when you put into a vector form, in a vector form, so we will take cross product. In a vector form, for example, the one that you see on the screen here is a different diagram compared to the previous one. So let's say this these particles move in the blue pathway, and it moves in a three-dimensional space. Just now, the previous one, this one is on the two-dimensional space, right? On a plane like a piece of paper. But when a piece of paper, you can directly take D multiplied by MV. But when it comes to three-dimensional, right, then you can take vector cross vector. For example, this particle move in a three-dimensional in a blue line, and the vector of your momentum is mv, pointing to the tangent direction of the pathway. And origin of O to the particles we label as R as a position. So you take your position, cross the mv, you get your angular momentum. So again, right hand rules. You use the right hand rules. So where is the direction of your angular momentum? You take the R, cross to the direction of your MV. So always your fingernails is your MV. So the R is like, okay, where does the R point to the momentum, right? So it's like building the arm. You see from here, the arrow and the MV, you form the arm, right? Like a 90-degree arm. So 90-degree arm will tell you the curve of your finger, right? So it will tell you that this one is anti-clockwise and to this direction following your thumb. Okay, so this is how you tell the direction of your angular momentum. Okay, so any question on this one? So there's a difference between the previous slide and this slide. So if you're moving in the 2D, then you can straight away use D cross the D times the momentum. But if you're in 3D, then you need to use vector products. Vector products. So you know that you can break your vector product in matrix form. Have you learned matrix? You learn matrix, right? So you can write the cross product into this form that you see on the screen. So the R here, you can break into X, Y, and Z length. So you can write in I, J, K in the matrix, and then Rx, Ry, Rz. Then same with the momentum. Momentum, MV, you can break into X direction, Y direction, and Z direction. Because this is, the one they see on the diagram here is the resultant of that vector. So you can split into X and Y and Z direction, okay? So how do you do this one? You need to go back to your mathematics lah. Okay, so you take this one, Rx multiplied by NV plus Ry multiplied by NV minus Rz minus NV. And then you do lah. Okay, so this is how you do. We won't go into the detail of the calculation. Okay, so the next one is the moment. If you have a three axis again, X, Y, and Z, and then there's a particle moving in a three-dimensional form. And this, there's a force acting on this particle, mean a loss of force, and then we sum all the force as sum of force that you see on the screen here, right? Then you will have a R distant from the origin to the particles, or position R from the origin, right? So how do we relate to what we learned so far? We always pull out chapter 2 equation, which is all the force you combine, it will give you motion. Not like your static chapter. When you come to engine dynamics, all the force acting on the particles or the rigid body, it will create motion. In this case, acceleration. So it give you defined by second Newton law, F equal to ma. Makes sense. All right. Then recall the definition of acceleration, which is v dot, or time differential of your velocity. Make sense? Okay. Then the moment of force about point O. Now you recall back what is the definition of moment. The moment of force and the R, you can use cross products. Again, moment, you use cross product again. Right hand rules. R cross F. R cross F. So this one is a three-dimensional, so you can use this one in the matrix form, right, if you want, but you use cross products, right? So again, what is force? Force is ma. Force equal to ma, a equal to v dot. V dot is time differential of your velocity. Makes sense? Then you continue, then you continue the equation. You refer to appendix C in the canvas. There is a cross product, how you derive the cross products, right? So at the end, your h dot, what I mean by h dot? Just now we define h angular momentum equal to r cross mv, right? Makes sense? And then you see there's a dot above the capital H here. It means you time differentiate the r cross mv. So do you see d over dt here? Okay. Next, this is a cross product. You know that when you do cross product, you freeze one of the term, you differentiate another one, plus you freeze this one, differentiate this one. Makes sense. So don't confuse by the notation you see on the screen here. Just recall what is a cross product. What is a chain rules. Okay. So the first one you get r dot cross mv plus r cross mv dot. Makes sense, huh? Okay. Then here we recall r dot cross mv, this one. You can group them. You can rewrite this one as m bracket r dot cross r dot in a vector form, right? But we won't go deep into how we prove this one. So r dot mv equal 0 because you cross the same vector, because it's go parallel, you'll get 0. There's no action if you do, So here you can cancel the first term. Okay. Then it arrives at h dot equal to r cross mv. So we can arrive that when you sum all the moment, it will equal to the change of your angular momentum. Right? You can see that above this equation, what is moment? You sum of moment equal to r cross mv. And then you can prove from the derivation of your angular momentum, r dot, the rate of change of your angular momentum, h dot, will still arrive at the same r cross mv. So the top equation will equal to the last equation. So left hand side equal to right hand side. This equation is called, okay, so this equation is called the relationship between moment of force and angular momentum. Okay, important. This is an important formula for today. You sum all the moment will equal to the angular momentum change. Okay, this is another how you link moment and angular momentum. Okay, this is moment, this is angular momentum. Okay, so this is a very important formula for chapter 4. Okay, so it works the same when you study about rigid body later. These the same things. Okay, makes sense so far, everything? Okay. Now let's look at how we solve, how we relate moment and angular momentum in this example. Okay. Now we go to example 9. Before you go into the question, you look at the diagram. The parcel was sliding on the slide here and with the R. So what kind of motion this box will experience? Linear or curvature? It's a collinear motion or curvature motion, right? So when curvature motion, you know what you need to do, right? You draw the tangent and normal axis. That's correct. Then after you draw normal tangent axis, what you do? What is the next formula you need to write? Acceleration, right? You write the acceleration equal an un plus at ut. Then you calculate what is an. An equal to V square over rho. What is VT? Sorry, AT. AT equal to V dot, right? Okay, so same. Here, you're given the R and theta and the velocity of the parcel. So a box, you're given the mass and given the smooth circular ramp. The word circular ramp, the word smooth, it means you don't need to consider friction. So all the free body diagram is important. When there's a contact surface, they always have what? Normal force. Then at the center of gravity, you always have a vertical go down W. Makes sense. Then if it's a free fall, there's no force acting on that. There's no cable tie. Of course, this one we tie with the, no, this one no cable, but I given you the R of the curvature. So this is the curvature motion, right? So you know that this curvature, so straight away draw what? Tangent, normal. Makes sense. Makes sense, right? Okay. So, and then, of course, if you want to calculate the friction, also can, but friction 0 here because it's smooth. So, friction. Okay. Now, you're given, and there's a typo error here, angle theta. On the slide, you see U with a typo error there. Determine the angular momentum about point O at this instant and the rate of increase of its speed. What is rate of increase in its speed? What is this? Acceleration. Okay, it is your AT. So before you solve, you try to think what equation related to this one. He asks you to find angular momentum. What is the angular momentum? Think of your right hand rules. What is right hand rules? R cross mv. Or in the scalar form, R times mv. Okay. So in here, you look at the diagram, there's R given, M given, V given. So free body diagram, like what I draw on the whiteboard, we draw the axis of T and N. You should be able to understand why T pointing this way and pointing this way already. Okay. Then there is the origin O and the R. Okay. So what is new for today is that you need to look at the diagram. If there's origin, normally when you look at angular moment or angular moment and sum of moment, normally there is a reference point. There's a reference point O. Example here. This is your O. Okay. So when you come see the question asks you about angular momentum, then add in your free body diagram, add in the reference point O, origin. Okay. Then theta this way, right? Same like that one. You can see, right, the angle is a zigzag relationship. Right. Then you put in the weight, always go down vertical, and the normal, and what else? You can split your R into x-axis and y-axis. Okay, x-axis and y-axis. So you know that your V is tangent to the path because it's a curve, right? So you calculate the angular momentum, which is R cross your MV. So in this case, this one, your D is your R. Where is the MV? Is the tangent direction, right? What is the direction? In this case, anticlockwise is the direction because R cross MV, right? So R cross MV is anticlockwise. And the direction is this way, right? Okay. So again, the fingernail of your hand is the direction of your moment. So in this way, R cross like this, R cross your one. Right. So you put in, and then the rate increase of speed is actually acceleration. So you use the relationship between moment and the rate of change of your angular momentum. That is what you learned in previous slides, right? So what is moment? Moment related to force only. All right. So how many force you have? Two force, normal and W. Normal do not create moment. There's no distance for it, right? Normal is along the R direction, so no moment. But the W you can split into Y and X direction, or radial and or normal direction or tangent direction, right? So when you split this one to tangent direction, when you have tangent direction times the distance 90 degree, you get moment. Okay, so W R sine theta Okay, my R sine, my line here should be slanted a little bit. My triangular should be parallel to my body. I draw something on the whiteboard here. My diagram should be like this. Can you see? It should be parallel to my surface. This one parallel to my surface. Okay, make correction on that. Then only you can find moment, because this line is 90 degree. Sorry, your yeah. Huh? So meaning the triangle should be inside the end. Okay, wait. W. Oh, correct. Means that means that the W here is on the normal x-axis. If you break this one to, no, it should be correct lah. This one, actually, you write the mg sine theta, then times the r, then you get the moment. So your W, this is W sine theta. Okay, then you times the R, you get the moment. Correct, on my slides is correct. No corrections is needed. So the moment on the left is you take the W sine theta, then you times the R, you get the moment. And what is the angular, the H dot? H dot is d over dt R mv. Makes sense? Okay, so you know that your R is constant, M is constant, so you can pull them out. This one, you pull R and M outside. So you see something on the screen here. So you can cancel the M, and then you can cancel the R, because R constant. So only you arrive at G sine theta equal to dv dt. Make sense? Okay. So once you have dv dt equal to sine, and then recall, use F equal to ma. So F equal to ma, you have two direction, normal and tangent direction. Okay. Then you put in what is the force in tangent direction. In this case, your force, the normal don't have, but the force is because of your W. So your W equal to mg sine theta. So this direction of tangent will equal to the motion moving on the slide here, right? Moving on this direction, tangent direction. Okay, so you can write W sine theta or mg sine theta equal to m dv dt. So here you can cancel m. Still you get dv dt g sine theta. This is a second approach if you use F equal to ma, chapter 2 equation. You can prove the one that you proved just now. You use a relationship of all the moment will equal to the rate of change of your angular momentum. Okay, there are two ways. One, if the question didn't mention anything and you see angular momentum inside question, the question expect you to use this relationship. And you can prove your answer by all the force equal to ma to find the missing, especially the A here. This one. Okay. And how do you find the V? If the question asks you find V, here you have dv dt equal to g sine theta. You move your dt to the right hand side. So you get dv equal to g sine theta dt. You know that you have dv dt, you can integrate. So here you will get v2 minus v1 minus, and this one you do integration. This one with the sign. So go back to the mathematics and sine will become cos and so on. So again, go home, practice this one. Might come out in your test too. Might come out in your test too. Go home, study what happens if you integrate sine theta. I do not show on my slides, but go home and look at the integration chapter, how to do sine integration. Okay, this one, example 9, do not have any value. Of course, when it comes to assessment, there will be a value over there. Okay, all right. Continue. Okay, so once we have definition of angular momentum and moment, we will go into principle. Previously, we have a few principle, right? Just recall. Chapter 1 don't have any principle. Chapter 2 don't have any principle. Chapter 2 is all the force equal to ma. Chapter 3 is one principle. What is the principle in your test one? Principle of work and energy. What is the principle of the energy look like? Change of work will equal to change of energy. Then you expand this one, right? So what is work? What is work? Integrate force. Yes. Yes, right? Okay, work is force times distance equal to kinetic 2 minus T1. Move this one, T1 plus integrate of FPS equal to T2. This is the first one. This is all the force. Means all the force inside a free body diagram will give you work. Just take note of this. Then all principle will have one conservation. What's the conservation of energy? What's the mean of conservation? Mean do not change. Conservation of energy means what? Energy before will equal to energy after. How many how many type of energy you have? Two. Kinetic plus potential equal to kinetic plus potential. This is the second conservation of energy in chapter 3. Chapter 4. What is the principle that you learn? Principle of impulse and momentum. Again, what is impulse? What is principle of impulse and momentum mentioned? Chain of impulse will equal to the change of momentum. Again, what is impulse? Integrate force dt equal to mv1 minus mv2. Sorry, mv2 minus mv1. We write this one, mv1 plus f dt equal to mv2. This one become your principle of impulse and momentum. Here, you also learn one more conservation. Conservation of momentum. Again, what is conservation? Something do not change. Here, we mention about momentum. So we tell you conservation of momentum means momentum do not change. So all the momentum before will equal to all the momentum after. So if you have one body, then mv1 equal to mv2. If one body, if two body, m1 v1 plus m2 v2 equal to m1 v12 plus m2 v22. Okay, so means this one is a velocity after. This is separate, means after bang, go to another direction. Okay, or separate. What happened if you coupled? Moment before still the same. You have two body, but when you coupled means you join together. Means you join the mass and same velocity. Okay, so this is conservation of momentum. Okay. This one impulse, and this one is called linear impulse. Before this, you learn about linear impulse mean move in a straight line. This morning, you learn about angular momentum. So use the same principle, but we apply angular impulse and momentum. It's actually, the long one is principle of angular impulse and angular momentum. Okay, so you learn about all the moment will equal to the rate of change of your angular momentum. All right, h is angular momentum. Dot there is a d, dt, and your angular momentum. All right, so we can write this one on the right hand side. H dot is 1 over dt h o. You move your dt to the left hand side. You know you can do integration. Every time you have a dt, you can do integration on the left hand side. Once you do at right hand side, left hand side also same. This is a change of your angular momentum. You rewrite the same. This equation is called principle of angular impulse and momentum. Derived from the relationship between moment and angular momentum. This one gives you principle of angular moment and momentum, right? Sorry, angular impulse, momentum. So you have the change of moment will equal to, not moment, the change of angular impulse will equal. Okay, what is angular impulse? Angular impulse, you take the momentum. Sorry, you take the momentum m. You times time, you get angular momentum. Okay, so angular impulse will equal to the change of your angular momentum. Okay, or you take this equation, the change of momentum left hand side will equal to the right hand side. But this one with the dot, you pull the dt to the left hand side. So you write the equation h1 plus integrate of a moment times time will equal to h2. This is a principle of angular impulse and momentum. Sorry, m dot d is impulse, angular impulse, not momentum. Angular impulse. Okay. Makes sense to you so far? Yeah. Okay. So, and you know that the middle one, what is moment? Moment is you take the R times the force, right? And you use the right hand rules. You always use right hand rules. D cross F, right? D cross F. How you form again? Use right hand rules. Refer to this shape. Look at your finger. How your finger can form this shape. So actually this way, right? So the moment is going inside the bob, and it is clockwise direction. So this one, you can transform your impulse, angular impulse, into R cross F. This is a cross product. Again, refer to the Canvas appendix. Go and see how to do cross products. Then, okay, see the same, replace the same. So if later you learn about rigid body, then you will still use the same, but you sum all the angular impulse, you sum all the angular momentum. Okay. So in vector form, just now, mv so this is in vector form. All the momentum is vector, all the force is vector. So you can write the first one is impulse, linear impulse and momentum, principle of linear impulse and momentum, right? This ft is impulse, but it's in linear form. But when it become angular, then you take h already. It's an angular momentum plus m dt is impulse already, right? Momentum times time, it become angular impulse equal to angular momentum after. Okay, so you know that vector is have a magnitude and direction, so you can break them into direction x, y, and z. Okay, same, same. So this one apply in your chapter 3, same, this one, sorry, chapter 3 is energy. Yeah. Okay, this one also can break into x, y, z direction. So all the principle will come with a pair of conservation. Okay, come with a conservation. So here, if conservation of angular momentum apply, so the impulse was gone, because impulse is what happened between, right? Conservation, we only look at what happened before and after angular momentum. So we have h1 will equal to h2. Okay, so this is called angular conservation of before and after. Okay, yeah. So when you need to apply this one, when you need to apply conservation, normally you look at before and after. You're not interested in what happened in the during the collision. You're not interested. You want to see before and after. Okay, let's look at example 10. Again, before you solve question, you look at the question. You can see whether this is a linear form or collinear form. So this one is a collinear form, right? So collinear form, you have the force there, it will create a normal and tangent reaction. So if the tractor force is given, and this force is in the equation form, right? So your F is no longer in a constant value, but your F equal to 150 t squared. Determine the speed of car when time is equal to 5 seconds. Car initially travel at a speed of 5 meters per second. Ignore the size. Okay, free body diagram, you draw the car. And in chapter 4, normally you go into 3-dimensional axis. So you have a Z, then you have an R, because you start to look into angular momentum and angular impulse. So you're dealing with R and no longer deal with S or rho and something, right? Then there is a curvature with the blue dot, although not perfect, but it's a curvature form, right? And there's a contact surface, then there's a normal acting between the tires and the path and the road. It's a 3D dimensional diagram. So weight pointing down, normal will always follow the condition of the surface. If the surface is slanted, then normal will always follow 90° to the surface, but the gravitational force will always pull down vertical, no matter how it changed the surface. Okay. Then there's a force pushing at the back of the machine, right? So you have two directions. One is the radial direction, force that pulling the, the radial direction. So you have a angular impulse that result from a weight, normal force, the radial friction force, right? Because the car, when you want to travel along the road, there is a force that prevent the car from sliding outside the circle. So there is a force, you can say as a friction force that, or resistance force that resists the car from go outside the curve of the road. So again, you see this one in chapter 4. You won't see this one in chapter 3 question. Come to chapter 4 question onwards, you will see 3-dimensional forces. Right, you apply principle of angular or impulse. Again, what is this? Angular impulse. What is angular impulse? What is the definition of angular impulse? Moment times time. Okay, angular impulse is moment times time. What is angular momentum? What is right-hand rules? Huh? Not force. What is momentum? Huh? mv. So R cross mv is your h. Okay. So again, don't confuse between moment and momentum. Okay. So angular, again, angular impulse is moment and time. Angular momentum, angular impulse is momentum, moment times time. Angular momentum is, you use your right hand rules, R cross mv. Right. So you look at angular momentum at z-axis, because if you look at this one, your mv is in this direction, right? Correct. So mv times the r cross mv, what is the direction? What's your right hand rules tell you? H pointing up or pointing down? Okay, so your mv is going this way, so it's r cross v, right? So then your z go up, huh? Okay. So you change your angular momentum, which is the r cross mv. So r mv in scalar form. All right. So r mv in the before, and then what is angular impulse? Moment, time. How to get your moment? The f and distance must be perpendicular. So this force is perpendicular to the radius all the time. Okay. Then what is angular momentum after? Angular momentum is position or distance times mv. So right hand rules. Okay. You substitute the value. RMC, R is 100 meter. M, in this case, 150 megagram. Again, take note, your coming assessment on the unit, we will always try to confuse you with unit. Use unit SI all the time. So you substitute the value, then you can solve. So the second one you don't know. Right? The second one you don't know. Then you put inside here. This one, you have the value. This one, you have one unknown. This one you can integrate. Right? Time is given 5 seconds. So 0 to 5. You integrate, you rearrange, solve the equation, you get velocity. He asks you to find the velocity after 5 seconds. 9 point something mega per second. Okay. This question also can solve by chapter 2 equation. Okay. However, if the question force you to use principle of angular impulse and momentum, you need to use this equation. If the question asks you to use principle of angular impulse and momentum in your calculation, you use chapter 2 equation, sorry, you get 0 marks for that component. Even though you arrive at the same, let's say in this example 10, you arrive at 9.17 velocity, you still get 0 point for that section, because you do not understand, you do not show your understanding in the principle of angular impulse and momentum. Okay, right? So I've given you a lot of time on this kind of warning. So don't come and see me say, sir, why I get the answer, but I do not, I still get 0 marks. You need to follow the instruction. If you don't understand, you don't show understanding, you don't show proof or evidence of understanding, we cannot give you marks. For example, this question come out lah. Then you have section A, section B, section C. Section A normally asks you to draw free body diagram. Section B, you will say, use the understanding in principle of angular impulse and momentum. Determine the speed of car when time equal to 5 seconds. Then you are forced to use principle of angular impulse momentum equation. But you will see question purposely ask you that, including your coming assessment, test 1. Okay. Again, if you test 1, you go and use principal angular impulse in your second question, then sorry, you get 0 marks. Your question 2 will be principle of work and energy. Now, you give me another principle, you also get 0 marks. Okay. Yeah. So this program is very direct. If you don't show any understanding, means you don't know, then you need to redo this module. We have to say sorry, please redo. All right. Okay. So, okay. See. Okay, we go for, I think this one is the last example. Yeah, this one is the last example. We go and then we stop the class. Okay, example 11. Example 11, you look at the diagram. You have some body tied to the center of the object, and then they given the axis O, right? So in chapter 4, in your free body diagram, again, you need to start putting in your origin O already. The 4 onwards, you need to show where is your reference axis. Either is Z, XYZ, or is a R or something. So you're given 2 kilogram disc, show rest on the smooth horizontal surface. Again, you only see smooth horizontal or smooth surface in tutorial question. You won't see in the final exam. Your final exam all will have friction force. So, but anyway, when you see object land on the surface, they always have a normal force. Just remind that. Okay, and attached to the elastic cord. What I mean by elastic means the cord can become longer and longer. You're given stiffness K. What is the spring equation? What is the force backed by the spring? How you calculate? Ax. What is the energy of the spring? Of kx squared. So initially unstretched, if the disk given velocity, initial velocity, perpendicular to the chord, you're given perpendicular chord. Determine the rate which the chord is being stretched and the speed of this at the instant of the chord stretch, 0.2 meter. You look at the diagram, this one move in this direction. Again, you look at the diagram, ask yourself, this is a rectilinear motion or collinear motion? We start linear or collinear? Why linear? What? No curve? You try to spin the object. How you move? It's a collinear motion. You move in a circle, right? So collinear. Okay, so you start with your free body diagram. You draw 3-dimensional. You put in the diagram. So before stretch is 0.5, given in the question. Okay, given in diagram. Then you move in the D1 1.5 in a tangent direction. Then it travel until one particular time where the elastic cord stretched to 0.2 meter. So you draw diagram. So this V2 is a tangent direction, but you can split into two directions. One is radial direction, one is angular direction. So you see this direction is along the radial or radius. This one is the change of angle. Okay, recall the chapter related with r and theta. I think this one is in chapter 3 or chapter 2. There's one chapter when we define the acceleration for r and theta. Then you put in the diagram, 0.5 stretch 0.2. Okay. Then W point down, normal, and there is a chord pointing in. Why direction point this way and not pointing out? Why? Why the force point inside and not point out? You still remember how I explained the spring? Object and the spring. How you draw the force direction? Do you remember? No, forget already. You imagine yourself as this object and you're being swing. What do you feel on your body? You tie to a rope, you're being swing. You feel being pulled or being pushed. So if you're this object, you swing in this direction, what do you feel? Push inside, right? Being pulled inside, right? Can you imagine? Can I? So the force will pull inside. So you have the free body diagram already. Then, because we are more interested in velocity, so velocity normally go to conservation. You interested in before and after. You don't interested in what is the impulse and everything, right? So angular momentum, again, what is momentum? Angular momentum. What is angular momentum? Ryan rules. MV, R cross MV. Yeah. So H1 equal to H2. So R MV 1 equal to R MV 2. Okay. In this case, okay. Okay. This VD2 is a resultant velocity. So when you split, you can say you have you can break into normal and tangent direction also, right? So you use the tangent velocity, which is V prime. That's why you see you're using MV in tangent direction with the R. Okay, and always 90 degree. R cross MV always 90 degree. That's why you do not use VD2 and you use V prime D2. Okay. You substitute the value. There's only one missing parameter. You solve, you get 1 point something. Okay. So once you get that one, you use conservation of energy. All right. So you might ask why I need to use conservation of energy when the question do not ask me to use this equation. Why I should use conservation energy? And this is chapter 4. Why I suddenly go and pull chapter 3 equation? Why? How many types of energy beside kinetic and potential? Kinetic, potential, and one more. Spring energy. These two, kinetic and potential, always don't involve spring. But you have see spring behavior, you need to remind yourself that actually one case that you can use potential, you can use energy, no? Because this one is stretchable. Stretchable, you see spring. Spring can create energy. Okay, before this, why you do not use spring? Because all the case you see before this don't have spring. This example, you seeing spring example. Yeah, before all this, the equation that you use conservation of energy, or you have, you don't have spring. There's one example at the last slides that I asked you to go home and read. That one is spring example. Go and read for your example 3. That one is important. Go and read. Okay, so here you put in why potential energy 0? In this case, why you do not include your potential energy? Huh? No different in? Right, okay. So the datum, the object always stay at your datum height, your Z. Huh? So there's no potential energy there. So you have mv, half mv square plus the spring energy before equal to after. Okay, now look carefully the question. When there's a spring, there's a stretchable items, consider spring energy inside the calculation. Okay. Try to think what happened if the question asks you, you're studying mechanical, you have wheel and absorber. Try to think. I give you hints already. Try to think how to solve system wheels with spring. Okay, at the end you get your video tool. Then this is the vector diagram. Once you find this one, you find this one, you have a v dash 2. You're able to find the magnitude of this one. Because why? How you find resultant? Square this one, square root. You get this one. Rearrange the equation, you get this one. Right? And by this, and also you're able to find the angle to the resultant. Okay. All right. Now for steady flow, it's not a focus of diploma, but you can use the principle of impulse and momentum to solve float problem. If you go into degree, you'll see this one when you do fluid mechanics or fluid dynamics or finite element analysis, right? So you go and read this for your information. Section 4.8, go and read. It's for your information. What I need to highlight is that it's still using principle of impulse and momentum. The idea still give the right hand rules, mv times the r equal to after, right? And the impulse inside here, you have the force acting on the body here. Force times time, you get impulse. And also, what is the impulse momentum? Moment times time, right? Angular momentum is moment times time. So how do you find moment? Force times the distance. So there's a force in the middle here, they give you impulse. All right. So you go and read. You're going to have a very lengthy equation with the cross products. And at the end, you use this equation with this rho VA or rho Q that you learn if you have anything linked with the fluid If you take fluid module this semester, then this is a very famous equation for you, right? The change of mass or mass flow rate will equal to rho VA equal to rho Q if you study fluid. Right? This is for fluid mechanics. For engine dynamics, F equal to ma is the core, or can say the king of equation in engine dynamics. F equal to ma. Okay, the rest you read. All the solution was given. And with this, we conclude chapter 4.